Imagine, for a second, two massive, incredibly expensive, and completely isolated islands. On one side, you've got a large language model. It's a total master of text and reasoning, but it's completely blind. Then, way over on the other island, you have a vision transformer. It can see every single pixel of an image flawlessly, but it can't speak a word or hold a conversation. Both are absolute powerhouses. And because they took a ridiculous amount of resources to build, their weights are what we call frozen. We literally cannot afford to retrain them from scratch. So how on earth do you build a bridge between the island of sight and the island of text without breaking the bank? Well, welcome to this explainer. Today, we're exploring one of the absolute most elegant solutions to this massive engineering headache, BLIP2, and a pretty ingenious piece of architecture known as the Q-former.
Okay, let's quickly hit our roadmap for solving this puzzle. We're going to cover 1. The VLM token bottleneck. 2. Meet the Q-former. 3. Two-stage pre-training. 4. Parameter economics. And finally 5. The 2026 modality split. Let's get into it.
Part 1. The VLM token bottleneck.
All right, so let's say you want to connect a frozen vision model, one that spits out 256 patch tokens, to a frozen 7 billion parameter LLM. If you try to just project those patches straight into the LLM using a naive linear layer, you're going to cause a massive traffic jam. I'm talking 8,192 tokens. Over a standard batch size of just 32 images, that is 8,192 tokens completely eaten up from your context window by the visual data alone. And you know, in the world of LLMs, context window space is absolutely premium real estate. We just can't afford to flood the prompt with that many uncompressed visual tokens just to look at a few images.
Which leads us to the ultimate BLIP2 question, and really the core engineering stakes for us today. Can we somehow compress that massive 256 token image representation down into something tiny while keeping all the crucial information the LLM needs to actually understand the image, answer questions, and reason about what it's seeing? And crucially, can we train this bridge from scratch without touching those giant frozen backbones?
Part 2. Meet the Q-former. Enter the hero of our story, the Q-former. It's a relatively small, 188 million parameter transformer that basically acts as the ultimate lightweight compression funnel. And the absolute magic trick that makes this whole thing tick: learnable queries. So instead of forcing the LLM to search through the entire image itself, the Q-former introduces 32 vectors. Think of them as a fixed set of 32 highly trained investigators. These investigators are parameters learned during training, and the exact same 32 investigators are sent in for every single image you feed into the model. Through a process called cross-attention, these 32 queries look out at the external image patches and pull out exactly what's needed.
The result? It's just pure compression magic. The Q-former successfully funnels those 256 raw image patches down into exactly 32 LLM-ready visual tokens. After going through the cross-attention layers, each one of those 32 queries walks away holding a tightly packed summary of the image. Maybe one query learns to encode the main objects, while another, focuses entirely on the background, or even counts the items. They don't have literal, hard-coded labels, but working together, these 32 queries compress all that complex visual info into a tiny, easily digestible package that just drops right into the LLM's text stream.
Part 3. Two-stage pre-training.
Now, having a slick bridge is completely useless if it doesn't actually know how to translate sight into text, right? So during stage 1 of pre-training, the really interesting thing to pay attention to is what is actually missing. There is absolutely no LLM involved yet. None. The vision model is completely frozen, and only the Q-former is training. It's essentially learning visual representation by juggling 3 distinct loss objectives at the exact same time. First up is ITC, or Image Text Contrastive Loss. This basically aligns the overall pooled image queries with the text. Next is ITM, Image Text Matching. That's a binary classifier that forces the queries to spot really fine-grained mismatches between an image and a caption. And finally, ITG, Image Grounded Text Generation, which literally forces the queries to encode information that can be successfully decoded into actual text. By mastering these 3 tasks, the Q-former gets a complete masterclass in visual representation.
So the whole brilliant trick here is this 2-step dance. Step 1 is all about representation learning, right? The Q-former trains completely alone to figure out the vision side. Then we hit step 2, generative learning. This is the big moment where we finally attach that massive frozen LLM, like an OPT or a Flynt T5 model. And to connect them, we just drop in a tiny linear projection layer to map our 32 queries perfectly to the LLM's dimension size. In this second stage, the only things that train are the Q-former and that tiny projection layer. The heavy LLM and the heavy vision model, they stay completely frozen the entire time.
Part 4. The parameter economics.
This incredibly careful, surgical strategy leads to some serious financial brilliance for AI engineers. The parameter economics of BLIP2 are, well, they're staggering. Listen to this. When it dropped, BLIP2 matched or even beat the massive Flamingo 80B model on zero-shot visual question answering, all while being 50 times smaller. Let's actually break that math down. You've got a 1.1 billion parameter frozen vision model, a 6.7 billion parameter frozen LLM, and our little trained Q-former sitting at just 188 million parameters. That means the trained bridge makes up roughly 2.4% of the entire stack's parameters. No joke. Instead of burning weeks fine-tuning a massive network end-to-end, engineers could train this bridge in a few days on a handful of GPUs. The cost savings are just enormous, and honestly, the quality speaks for itself.
Part 5. The 2026 Modality Split. But, the field of AI moves at light speed. As engineers kept pushing the limits, a massive divergence happened. As visual instruction data started getting really, really good, a totally competing philosophy emerged, basically championed by models like Lava. Lava actually looked at the Q-former's elegant compression and just abandoned it completely. Instead of compressing everything down to 32 tokens, Lava uses a simple MLP projector to pass all 576 raw image patches straight into the LLM. Why would they do that? Well, it turns out that if you have incredibly high-quality instruction data, letting the LLM attend over all those raw, uncompressed patches actually gives you better fine-grained visual quality. So we're left with this ultimate trade-off. BLIP2 and the Q-former optimize strictly for your token budget, keeping things nice and light. Lava, on the other hand, optimizes for raw visual quality, but man, it fills up your context window incredibly fast.
And because of that massive trade-off, the modern landscape basically fractured into 4 distinct architectural descendants that engineers are choosing between today. First up, you have the Q-former models like BLIP2 and InstructBLIP, which absolutely dominate whenever token budgets are tight, like if you're processing long videos. Second is the perceiver resampler, sort of a cousin to the Q-former, used in models like Flamingo and IDEFIX. Third, we have the MLP projector, which is loved by Lava and Cambrian 1 for that sweet, high raw quality. And finally, the attention pool method, which you'll see in Vila and Polygamma. And look, all 4 of these are completely valid ways to build that bridge between sight and text.
Which brings us to the end of our explainer, and honestly, to a pretty massive question that you are going to have to answer on your next AI build. When you are looking to bridge this modality gap, you really have to ask yourself, what exactly is your constraint? Do you have a super strict token budget where you desperately need the brilliant compression of a Q-former? Or is your priority raw quality per token, where something like an MLP projector is going to serve you a lot better? The bridge you choose literally changes everything about how your model sees the world. Thanks for hanging out with me for this explainer. Keep building, and I will see you next time.